Hello and welcome to the second lecture on machine learning. Today we'll further delve into supervised and unsupervised learning settings and specifically start building up the story of method of least squares, the simplest example of a machine learning problem, which is the curve fitting problem. So recall that we very briefly introduced the concepts of supervised and unsupervised learning. Today we'll further illustrate these concepts with examples. Suppose you are given a basket of fresh fruits and you are asked to identify the type of each fruit in the basket. So the types could be apple, banana, cherry or grape. Now, your task could be simpler if you had observations such as the size, the shape, or the color of these fruits. In addition, you might be also told for a sample basket the label or the type of each fruit in the basket. This is what we would refer to as a trained data. The goal in this case of supervised learning is to develop an ability to assign labels to new fruits based on observations that you make on them. So what would be the observations? For a new fruit, you would again observe the size, in this specific case parameterized by length, breadth, shape, color, and so on. And based on these observations, you try and predict what the label of the fruit is. And in doing so, you would make use of the training data, which consists of fruits and their observations with the true label. So this is the supervised learning setting. Achieve the goal by learning from the trained data. We could also consider another case where you don't have a trained data. That is, you are not provided any label on each of the fruits. Now could you organize the basket? Please note the difference. We are not talking about labeling, but we are saying, can you organize the basket by clubbing together fruits of the same type? What does this mean? It means, well, I have this big basket. I would try and get some of these fruits which are of the same type on one end, maybe some other fruits which are of similar type at the other end. What does this mean? Well, practically this means that you would group together fruits with similar shapes or sizes. So you note that fruits on this corner have similar shapes and that are markedly different from the shape of fruits on the other corner. So for example, if you were to group the fruits mentioned earlier on the basis of color, you would actually find that apples and cherry tend to come together because they are red, and bananas and grapes tend to be clubbed together because they are greenish. On the other hand, if you were to group the fruits based on size, you would find two groups. The big group would consist of apple and banana, and the small one would consist of cherry and grapes. Now, by taking a combination of these two attributes or observations, which is color and size, you can uniquely identify each of these four fruits. Of course, there are several other fruits which are green in color and small in size, and there are several other fruits which are also red in color and big in size. So it is only in this simple setting of 4 types of fruits that the combination of these 2 attributes helps you identify each fruit uniquely. This process of organizing based on grouping of types or entities which have similar attributes is called unsupervised learning. Please note that in this setting, you are completely dependent on the choice of the observations or attributes. In this case, color and size. If you didn't know the size, or if you were not able to observe the color of the fruits, you would get a very different grouping. So the key difference between supervised and unsupervised learning is that in supervised learning, you are provided the desired observed output. This is specified in the sample. Going back to our previous case, you were provided the label which was the name of fruit or name of type of the fruit on each instance of the fruit. In the unsupervised learning case, your desired output is unobserved or unspecified. So the unsupervised learning case, you're kind of left guessing as to how these different instances should be grouped based on a hidden or unobserved label. Notice that in the case of supervised learning, providing the label incurs some cost. So there is no free lunch. Either you pay the price of providing manual labels or you incur uncertainty or computational overheads in dealing with these entities which have hidden or unobserved labels. So we revisit the different types of machine learning problems, but now very specifically we identify 3 canonical learning settings. The first is regression, which is an instance of supervised learning. For example, you might be interested in predicting the height of a student as a function of his weight or vice versa. You might also want to estimate an unobserved variable in terms of multiple observations. For example, you might want to predict the temperature as a function of multiple observations, which could include the time of the year, the latitude, the longitude, and so on. The other canonical example is the classification setting, which is again a supervised learning setting. As an example, you might be provided handwritten digits along with their labels. So you might be told that these are all instances of 0, these are instances of 2, and so on. And based on these labels, you want to be able to predict what a new handwritten digit is. More simply, you can plot these digits in some dimensional space, in this case a two-dimensional space, and if you observe that points with similar color, just similar label, seem to appear in one section of the space, you would be somewhat confident in developing a model that identifies this section and associates it with a corresponding colored label. That's what you see on the right hand side. This section has been identified as corresponding to red color, this section to the green color, and this to the blue color. The third example is unsupervised learning, where you are actually not provided the colors. So imagine that the colors are not provided on the left hand side. What would you do? You'd still observe that the points in this section are all clustered together, and there is a good amount of separation from this cluster, between this cluster and the other clusters. And similarly, there is good separation between this cluster and the other two clusters, and so on. So you identify three clusters based on a notion of separatedness. This is an example of clustering. However, there are several other instances of unsupervised learning. One very common and extremely useful setting is that of dimensionality reduction, where you have provided points in some high dimensional data, in this case it's 2 dimensions, and you are trying to find a lower dimensional representation of this space. So this is a lower dimensional representation. And why do I say so? Well, I say so because you could characterize this curve as a quadratic curve, which could have an equation ax square plus bx plus c. So whereas in the left hand side you had to explicitly provide the x coordinate and y coordinate for each of these points, in the right hand side all you need to do is provide the x coordinate, and the y coordinate is computed using this approximate formula ax square plus bx plus c for some appropriate choice of a, b and c. So this is a case of dimensionality reduction. Interestingly, the setting of dimensionality reduction comes very close to the first problem that we will discuss in this course, and that is of least square regression. So more formally, supervised learning is the problem of looking at data which is in the form of tuples xi and yi. Xi is the input, yi is the observed output, and you actually desire to be able to predict this output for new instances. In order to achieve that, you factor in the entire training data and try and learn a function. Now this function f, which you try to learn, might belong to a large function space. One example of this function space is the linear function space. And we will consider this example linear function space in our following lectures. And we will consider this linear function space in the immediate examples to follow. The goal is make use of this learning process and predict effectively and accurately on new unseen examples.